All right, hi folks. I wanted to show you a little bit more detail about calorimetry problems. Since we don't have a ton of time in class, get ourselves aimed here a little bit. Well, I won't go above that. You can see it says metal, water, and calorimeter. When you're setting up a calorimetry problem such as this, you want to make sure that you make a chart for every problem. They're very complicated. So it's a lot easier if you use a chart to keep track of all your data. Just imagine metal, water, and the third column is calorimeter. So we're going to do the first calorimetry problem right now. It says a mass of zinc with a specific heat of 0.3879 joules per gram degree Celsius, mass of 110.53 grams, is heated to 100.0 degrees Celsius in boiling water. It's placed into a calorimeter with a mass of 7.00 grams, specific heat of 1.40 joules per gram degree Celsius, containing water of a temperature 24.0 degrees Celsius. Once the contents reach equilibrium, all the same temperature, the metal, the water, and the calorimeter all will end up the same temperature. And that temperature is 26.0 degrees Celsius. What is the mass of the water in the calorimeter? Ignore the calorimeter and then find the mass of the water again. That will just help you to see that significant figures-wise, the kind of calorimeters that we used in class do not have any impact or very, very little impact on the answer that you get. So what do we know in the problem? We'll fill in our chart with what we know. So we know that we have a metal of the mass 110.53 grams. We know the specific heat of that metal, which is zinc, is 0.3879 joules per gram degrees Celsius. Every piece of zinc everywhere has that same specific heat. We know that our metal comes out of boiling water with a temperature, initial temperature of 100.0 degrees Celsius. We know that the final temperature for everything is 26.0 degrees Celsius, because our goal in calorimetry is to get all of our components to the same temperature, to an equilibrium temperature. Well, we'll change colors for all of these guys. So we can find our change in temperature, which will be temperature final minus temperature initial. Obviously, the metal is going to be losing temperature, so we're going to end up with a negative 74.0 degrees Celsius. Temperature final minus temperature initial. Okay, moving on to what do we know about the water? Well, for water, we know we want to find the mass. That's the goal of the problem. We know specific heat of water is 4.184 joules per gram degrees Celsius. We know that our initial temperature is, initial temperature is given as 24.0 degrees Celsius. We know that the entire system ends the experiment at 26.0 degrees Celsius. So we can find our change in temperature, which will be a positive 2.0 degrees Celsius. The water was heated up a little bit by the heat lost by the metal. What do we know about our calorimeter? Okay, we know the mass is 7.0 grams. We know the specific heat is 1.40 joules per gram degrees Celsius. We know that it's always going to have the same temperature data as the water. It ends at 26.0 degrees Celsius, started out at 24.0 degrees Celsius. So we're assuming that just like the water, the calorimeter increased in temperature by 2 degrees Celsius. That's our change in temperature. Okay, so now that we know all that, what can we work on first? We should always work on what we know the most about. Ooh, dear, I put wrong stuff in there. All right, sorry. Q of the metal, we don't know yet. We do know the specific heat of the metal is what I wrote up there. 3.879 joules per gram degrees Celsius. Okay, so what do we know the most about? Well, we know lots about the metal, lots about the calorimeter. So we should be able to calculate the heat lost by the metal and the heat gained by the calorimeter. So we'll start with the metal. We use our calorimetry equation, Q equals M times C times delta T. Heat is mass times specific heat times change in temperature. Okay, so we can look over here, say we don't know the heat of the metal, we need to find out. We do know the mass of the metal is 110.53 grams. Specific heat is 0.3879 joules per gram degrees Celsius. Temperature change for the metal is negative 74.0 degrees, and that's in Celsius, which doesn't really fit. Let me see if that'll fit on the board. Yep, okay, we have it all on film. Okay, so if I type that into my calculator, I find that the heat that the metal lost is going to be negative because my temperature changes in negative. And it comes out to, let's see, negative 3,170 joules. If you think about significant figures, you have 5 in the mass, 4 in the specific heat, only 3 in the temperature. So we have to run to 3 significant figures. 3,170 has 3 significant figures, so that's good. So then we can find also for the calorimeter, I'll go in green since our calorimeter is green. We have enough information to find the heat gained by the calorimeter. So that would be Q equals mass, 7.0 grams, times specific heat, 1.40 joules per gram degrees Celsius, times change in temperature, which is 2.0 degrees Celsius. That's for the calorimeter. So the heat gained by the calorimeter is going to come out when you type that in to 20 joules. If we look at significant figures, we have 2 here, 3 here, 2 here. So this is actually significant. We need to have 2 significant digits because there are 2 here and 3 here. We can round to 2. So to write that for significant figure purposes, you would have to write 2.0 times 10 to the 1 joules to show that both are significant. I'll put the little line under the 20 to show that it is significant if I'm trying to fit it on the board here. All right, so I'm going to pause and cut to the next video so we can fit it on YouTube. See you in a moment.